Hello and welcome. Today is the day first of fifth week of this course. So in the last week we learned about the great orthogonality theorem and its consequences, and we also tried to use those consequences of the great orthogonality theorem to find out the character table of two simple point groups, namely C2V and C3V. So what we will start with today is to take a most comprehensive example of how we can use the great orthogonality theorem and the rules that come out as consequences of that theorem to form the character table, the complete character table, what I mean, because in the previous class we learned about how to find out the irreducible representations and their terminal, their Mulliken symbols. But today we will try to derive the whole character table. That means including the area 3 and area 4. If you remember, a character table has 4 different segments, area 1, 2, 3 and 4. So we will start with a molecule which is like M stands for metal, having its charge, and you have 4 bidentate ligand, okay, of type this, okay, for example ethylene diamine. So while solving this problem, we will use all the knowledges that we have so far acquired throughout this course. Okay, so this example is going to give you an overall idea that how to use the symmetry and the the theories of group the theorems of group theory help you finding out the character table, the total character table of any given molecule. So first question that we have to ask, what is the point group of this particular type of molecule? And in order to do that, we need to find out that what are the symmetry operations. Okay, our first symmetry elements. And therefore, the symmetry operations generated from that. So what are the different symmetry elements that are present here? So in order to find it out, we need to know the structure of the molecule. So if I draw in a proper way, that will help me finding out the symmetry elements that this particular molecular structure can have. So let me do that real quick. So this is going to be pretty similar to the case of the COEN whole 3. Okay. So let me put the ligands here. Maybe I will use a different color. So you have to remember that these are the bidentate ligands, and here we are ignoring the charge. So right, so this is how we can represent this molecule. So here you can easily figure out that there is a C4 axis, which is the principal axis of symmetry. So this is the C4 axis. So I have one C4 axis of symmetry, and if I take this as Z axis, I can also say that this is C4Z. So I can even specify this one. Okay, and we will figure out what are the symmetry operations that can be generated, and by now you should be able to do that real quick. So what are the other elements that are possible here? So you can imagine an axis which is perpendicular to this CZ, which will flip this molecule, okay, if I rotate by 180 degree about this axis. So this will be a perpendicular C2. Similarly, I can find another perpendicular C2 in this direction. Okay, so we have got two perpendicular C2s. Now it is also possible to find the perpendicular C2s along the diagonal of this first square, you can see. Okay, so this is another C2. So we have got 4 C2s which are perpendicular to the principal axis, that is C4 here. All right, so I have got total 4 C2s which are perpendicular to C4. Are there any other symmetry element? There is nothing else apart from the identity, which is implied, always it will be there. So now identity will generate only one operations identity, and this C4 will generate C4 2, C4 3, and C4 4 is identity. Now C4 2 is nothing but rotated axis, same Z axis, by 180 degree. Okay, so this one I can write as C2 along Z axis. Okay, so this is also along Z. Now there are 4 C2 which are perpendicular to C4. They are along this 4 axis. So each C2 will generate only one operation, because C2 operated twice will generate identity. So these are the all symmetry operations that are possible for this point, this particular molecule. So then what is the point group of this molecule, right? So we know how to find out the point group of any given molecular structure if we know the symmetry operations. We now know the symmetry operations. So this molecule, if I look at their symmetry operations, it clearly tells that it does not belong to any of the spatial groups. Neither it has multiple principal axis of rotation symmetry, neither it belongs to linear molecule, neither it has only inverse or only sigma as the elements that are present, and therefore we directly go, if you remember, to step 4 and step 5, which we used to classify the molecules into point groups. So therefore I have a principal axis of symmetry which is single principal axis of symmetry and not mere consequence of the improper axis of symmetry. So next question will be, are there n number of perpendicular C2s to this Cn? So we have, yes, this is C4 and we have 4 C2 perpendicular to that C4. So therefore it belongs to D type of point group. Not only that, it's specifically D4 type. And next question that we ask, are there any sigma H? Answer is no. Next question we ask, are there any sigma V's? That is also no. So therefore this is the point group. Okay, so I have got my point group for this particular molecule, which is D4. Okay, so now knowing that, we will try to find out the character table of this particular point group D4. So let's do that now. So in order to find the character table, first we have to find out the classes, right? So what will be the what are the classes that are present here. Let's have a look at that first. So identity will form a class by itself. Now, if you do a similarity transformation on this each of the symmetry operations of this point group, you will find out what are the different symmetry operations belonging to particular class. Okay, so, or which particular symmetry operations form class together or class by itself. So now C4 and C4(3) they form a class. Okay, in some previous examples we have seen that, while C4(2) forms a class by itself. Okay, because if you intuitively you can easily figure this out. This C4(2) is nothing but C2, and C2 when you operate twice it will give identity. Now, this particular C2 is a unique type of C2 for this particular molecule. There are other C2s, but those C2s are completely different from this one. So, this particular C2, which is C2Z, is not going to be clubbed together with any other C2s. Therefore, this C4(2) or C2Z will form a class by itself. Okay. So, next I have class for C4, which combines C4 and C4(3). So, I have two elements in that particular class, and we also said about C2Z, right. Now, we are left with 4 other C2s which are perpendicular to C4. Now, if you remember, when I drew the C2s, there are 2 different types of C2s here also. Okay. So, 2 of the C2s, they were along the diagonal of the front square that I drew, while the other 2 C2, they were along the diagonal of the square that I drew, which was behind the plane of the first square. Okay. So, 2 C2s will form a class and another 2 C2s will form another class. So, therefore, I can differentiate them. So, for example, if I just quickly redraw the structure, so something like that, and right. So, we had C2s which was along this as well as this. Now, you can use C4 to take this particular axis over here. So, therefore, this C2, if I called this is as C2, suppose this is my C2x, then this will be my C2y, right. So, C2x can be converted into or transformed into C2y. Therefore, C2x and C2y are equivalent, and we also know that equivalent operations form class. So, therefore, C2x and C2y will form a class which I can write as 2C2. Similarly, the other 2 axes which are along this diagonal and this diagonal, they will also form a class, right. So, if I call this as x and this as y, then I will call this one as C2 say xy, maybe I can separate them C2 prime, and this one let me call as C2 x, C2 prime xy bar to differentiate. Now, in that case, these 2 C2 primes will form a class, because similar to this C2x and C2y, this C2 primes, they are also equivalent. So, let me write this as 2 C2 primes. Okay. And since the characters of the symmetry character of the representation for a symmetry operation belonging to one class will be identical to another element also belonging to the same class. So, if I find the character of the representation for one of them, I automatically have for the other one. So, we will also look for only one of this, either C2x or C2y. Fine. Similarly, here we will only look for C2 prime xy or C2 prime xy bar. So, having this idea, let's try to form the character table. So, what is the order of the group here? We have the order of group here as h equals to 8, right? Now, how many irreducible representation it can have? It will be equal to the number of classes that are possible, that we got from the consequence of the great orthogonality theorem. So, we have 1, 2, 3, 4, 5 classes. So, number of classes equals to 5. Therefore, the number of irreducible representation is also 5. So, I can write there will be gamma 1, gamma 2, gamma 3, gamma 4 and gamma 5. Okay. So far we do not have any idea what is the nature of the irreducible representation. Therefore, we are just giving them a general name in terms of gammas. Now, what about the dimensionalities of these irreducible representations? So, then if we go back to those rules that we got out of the great orthogonality theorem, then we can say that summation over I Li square equals to the order of the group, right. So, in our case what we have 5 different irreducible representation. So, L1, L2, L3, L4, L5 equals to 8. That is our equation. So, what are the different ways I can form? Remember, L has to be positive and should be greater than 0 for sure. So, L cannot be 0 and L has to be positive. So, if I assign all of them as 1, then I have 5 which is less than 8. So, that is not a solution. In case I make one of them as 2, then I have got 4 plus 4 equals to 8, and that seems to be the unique solution, because if I make 2 of them as 2, then already I have got total 8, and then rest of them will be minimum 1. So, total sum will cross 8. So, our unique solution is that L1 equals to 1, L2 equals to 1, L3 equals to 1, L4 equals to 1 and L5 equals to 8, which makes this equation satisfied. Therefore, these 4 are one-dimensional irreducible representation and this 5th one is a two-dimensional representation. All right. Now, we also know that for a given character table of any point group, there will be one totally symmetric irreducible representation, right, for which all the characters are plus 1, and we can write down that for gamma 1. So, let us fill this row, all right. Quickly let us check that if the square of the characters corresponding to each symmetry operations for one IR is equal to the order of the group or not. So, if you do that, so 1 plus 2 into 1 plus 1 plus 2 into 1 plus 2 into 1, yes, that is equals to 8. So, this is satisfied. Now, what else we know so far? That there are 4 one-dimensional irreducible representation and one two-dimensional representation. So, dimensionality is given by the character. Dimensionality of any representation, reducible or irreducible, is given by the character of corresponding to the identity operation. Okay. So, this much we can write. Now, we have to fill out the rest of the places. So, regarding the one-dimensional irreducible representation, we can very easily do that, because what we have to consider is that any two irreducible representation will be orthogonal until unless we are considering the same irreducible representation. So, gamma 1 and gamma 2 will be orthogonal, gamma 2, gamma 3 will be orthogonal. So, any one of any two of them, if we pick, they will be orthogonal to each other. So, if we keep that in mind, then we can easily fill this place at least up to gamma 4. So, let us do that. So, total we have 8 operations, okay, and these are all one-dimensional IRs. So, what I have to do, if I have to make them orthogonal, say we already have this totally symmetric irreducible representation. So, if I want to form another irreducible representation which is orthogonal to this, what I have to do, I have to make 4 of the operations having character +1, while the other 4 will have -1 as character. So, if I do that, very simply I can get it. So, here I have 4 operations, I will ascribe +1 to it, and there we have another 4 which I ascribe -1 to this. So, this will again satisfy the clause of the sum of the dimension square of the IR will give you sum of the characters of the IR will give you the order of the group, because square of any negative quantity will give you a positive quantity. So, I got 1, and then I can keep filling. So, let me do this one. So, I have 2 plus 2, 4 negative ones, and other 4 are positive. Okay. So, let me just interchange these two. All right. So, now if you quickly verify if they are orthogonal or not, you can find that out. So, let us say I am looking for gamma 3 and gamma 4. Okay. So, if I make a product between the characters of gamma 3 and gamma 4 on one-to-one basis, okay. So, what I am going to do is gamma 3 and gamma 4. This type of product, which I already have this used in my last class, this kind of product is known as direct product. Okay. A few important things about this direct product will be discussed in the following class or the next to next class. However, so in this particular type of product, which is direct product, we have one-to-one multiplication. Okay. So, what we have here, we have, if I write in terms of a direct product, we do it very similar to the character table. So, we have 2C4, C2Z, C2X or C2Y, and then C2 primes. Okay. So, if we multiply 1 into 1, I have 1, -1 and -1, I have +1, then 1 and 1, it gives me +1, then 1 and minus 1, it gives me minus 1, and this one gives me minus 1. Okay. So, if I have a sum of all these quantities at the end, so I will have 1 plus 2 into 1 plus 1 plus 2 into minus 1 plus 2 into minus 1, which is equals to 0. This proves the orthogonality. You can take any two irreducible representation and you can verify this orthogonality relation between the irreducible representation, which is also telling you that okay, so far whatever you have got for gamma 1 to gamma 4, they are correct. So, each of them are normalized to the order of the group, and any two IRs are orthogonal to each other. So, they are forming an orthonormal set. Now, the next thing that we are left with is to find out about this two-dimensional irreducible representation. So, one way to do this is to try out, so like doing a trial and error method, if you find some numbers which will be orthogonal to each of this. Okay. Otherwise, there is a very easy solution where you can take any generalized point, okay, and take its coordinates, and then you apply all the symmetry operations and get the representation. So, for example, if I take a coordinate system as x, y and z, and then minus x, minus y, minus z, you can suppose this is my general point whose coordinates are given by x, y, z. So, if I apply all these operations, okay, so my C4 is along the z axis. Okay. Now, one important thing is that the z axis remains unchanged. Okay. So, under most of these operations, and under certain but whatever be the case, z axis can independently form an irreducible representation, and therefore, this will give you an one-dimensional representation. So, one-dimensional representation for this particular group we have already found, and we are looking for the two-dimensional representation. So, we have already seen in certain cases that x and y, they transform together, okay, and you can separate out z and xy. So, here also we will do the same thing. So, we will omit z and we will perform our work on x and y, all right. So, my C4 is along this direction, and if I perform C4 on my x and y basis, what I am going to get? So, here suppose I rotate, then x will go to place of y and y will go to the place of minus x, right. So, if you form a matrix for this C4, you can do that very easily, because upon the operation of C4 on x, x is becoming y, right. So, this will be y is becoming minus x, fine. So, this will becoming so this is my matrix for C4, all right. And then we can have the matrix. So, this will give you the character of the representation, which is 0. Now, if we look at the representation for C to Z, what we are going to get? We are going to get x getting transformed into minus x and y getting transformed into minus y. So, what we have is this. Fine. So, if I look at the character for this one, this is equals to minus 2. Okay. Next, we have C2, that is C2x or C2y. So, let us take this is as C2x. If I find C2x, our character for C2y will be also the same because they belong to the same class. So, what does C2x do? So, C2x is along x axis, right? So, it will do nothing to x axis, but it will transform y to minus y, correct? So, you can find out that x is remaining same while y is becoming minus 1. Okay. So, therefore, the chi equals to 0. All right. And for C2 prime, if I take C2 prime as C2 xy, so if I call this one as xy, so if I can redraw this one without this z, so if I have x and y, then this, if I call C2 prime xy, then what it will do? It will transform x into y and y into x, correct? So, C2 prime xy, it will transform x into y and y into x, correct? So, that means I have this. So, we have got for these 4 operations, and identity we know it is always going to be an unit matrix. So, we are talking about 2 basis functions. So, the dimensionality will be 2. So, I have an unit matrix of rank 2. So, these are the matrices and the corresponding characters are here. So, character of E is equals to 2. So, we will stop here today, and the next class we will start from right here and complete the character table. Thank you so much.